Hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel, Linea MCTI. Today, we have the great honor of having Dr. Renu Malhotra, a professor of planetary sciences from the University of Arizona. Dr. Malhotra has revolutionized our understanding of the history of the solar system by using the orbital resonance between Pluto and Neptune to infer large-scale orbital migration of the giant planets and to predict the existence of the Plutinos and other small planets in resonance with Neptune. Her work in planetary dynamics has spanned a wide variety of topics, including extrasolar planets and debris disks around nearby stars, the formation and evolution of the Kuiper belt and the asteroid belt, the orbital resonances amongst the moons of the giant planets, and the meteoritic bombardment history of the planets. Dr. Malhotra, thank you for being so kind and having accepted to give us a webinar talk today on such interesting topics. The floor is yours.
Thank you, Tasia. Welcome, everybody. What I'm going to talk about today is, the title of the talk is Pluto Near the Edge of Strong Chaos. I'm going to give you a background about this problem, and that's in a nutshell. What it is that Pluto's orbit is known to be weakly chaotic, but it is stable on timescales comparable to the age of the solar system, even longer. Pluto has had a pretty crucial role in revealing the orbital migration history of the planets through its orbital resonance with Neptune. And however, many properties of Pluto's orbital dynamics are only partially understood. So today I'm going to share with you some new results on the role of Jupiter, Saturn, and Uranus on Pluto's long-term orbital stability. So we've known about the role of Neptune on Pluto's stability for a long time. The role of the other planets has been less well understood. So what we found, so the results I'm going to share, the new results, have been published in this paper that you see the citation at the bottom. My co-author on that is Takashi Ito from Japan, the National Optical Observatories of Japan. And in a nutshell, what we found was that Jupiter and Saturn and Uranus have a special or fortuitous orbital arrangement that defines a zone of stability for Pluto-like orbits. It's a narrow zone. It's bounded by strong chaos. And this was not well understood previously. As I said, the role of Neptune was better understood. So let's see, am I able to forward my slides? Yes. So going back to the 1990s, our picture of the solar system was that there were 9 planets in the solar system, and here's a sketch that you would find in textbooks of that era. But the 9th planet, Pluto, did not fit in as well. Its orbit is highly elliptical compared to the relatively circular orbits of the other planets, and it's also kind of tilted out of the mutual plane of the other planets. And just to give you a big picture of the solar system, because many of you probably are outside of solar system astronomy, here's a sketch that I like to show of the solar system, the big picture. Here we have the planets. We have the small bodies and these little dots. So the planets keep their distance from the sun more or less the same because their orbits are pretty circular. We, of course, are over here. Here's the scale. Here, and this is 1 astronomical unit where we are here on Earth. Neptune is out at 30 astronomical units. Pluto's orbit spans this big range. As you can see, it goes from its perihelion is inside, its interior to the distance of Neptune, and its aphelion is almost twice as far away. And then all these small dots over here are the Kuiper belt, and today we know that Pluto is a dwarf planet and part of this population of minor planets known as the Kuiper belt. And then surrounding the solar system is this Oort cloud of comets, which is more or less isotropically distributed around the solar system. going roughly halfway to the nearest stars. Okay, so then let's look at Pluto. Pluto is eccentric, and that's meant to be partially a pun. Its orbital path overlaps that of Neptune, so its perihelion distance occurs inside of Neptune. Here's a top-down view of Neptune's orbit and Pluto's orbit. And Pluto's aphelion is roughly, as I said, about twice as far as Neptune is from the sun. And looking sideways, we can see that Pluto's orbit plane is tilted to that of the plane of the other planets. And that tilt is around 17 degrees, and it's rather large. And that was actually big part of the motivation of the current work that I'm going to share. Now, despite its overlap with Neptune's orbit, Pluto is not in any danger of colliding with Neptune. That was an initial fear. When Pluto was first discovered, it was thought, oh, its orbit is overlapping that of Neptune's, and there might be times when it would have close encounters with Neptune and get greatly disturbed. And then later on, as its orbit was refined, it was realized that it's not in any danger of having any close approaches to Neptune because it's shielded, it's protected from those by this orbital resonance condition. So its orbit period is almost exactly 1.5 times Neptune's orbit period. As Neptune goes around 3 times, Pluto goes around 2 times around the sun. And if you look in frame rotating with Neptune around the sun, so Neptune is nearly stationary there. You can see it's doing this little jiggle. In that frame, Pluto does this retrograde path, and it's these loops that you see, these little loops, are its perihelion loops. When it reaches perihelion, it is roughly 90 degrees away from Neptune, and that location of perihelion oscillates, and that's called a libration. We'll look at that in a little bit more. There's numerical evidence that Pluto is chaotic. If we take the whole solar system and propagate the orbits of the planets and Pluto for a long period of time, this was done for the longest period back in 1988. This was one of the first long-term integrations of the solar system that became possible with digital computers. And Jerry Sussman and Jack Wisdom did this orbital propagation for 845 million years. Okay, and what they did was they took not only Pluto but also a little shadow particle, another Pluto-like object, a test particle, shadowing Pluto's orbit, and found that the two Plutos would diverge exponentially with time with an astonishingly short period of time, 20 million years. And that's the hallmark of a chaotic orbit, dynamical chaos, this exponential divergence of orbits with very small differences in initial conditions. And so now this was rather an astonishing result, that Pluto's orbit is chaotic with a very short e-folding time. But subsequently, many other, I should say, this was the first detection of chaos in the solar system. Since then, we've discovered chaos in a number of different contexts in the solar system. Most small bodies have chaotic orbits. The solar system itself is technically chaotic. It has this exponential divergence as a whole, all the planets' orbits as well. But they're really weak. That chaos is not very potent, so to speak, in changing a whole lot in the overall architecture of the solar system. What I'm showing you here is a paper, an abstract of a paper by an Italian group that was published shortly after the Sussman and Wisdom paper. This group had also been working on long-term integrations of the solar system, and they had done this independent integration, propagation for 100 million years, and they found the opposite, more or less. Not quite the opposite, but they found that there was no instability, there was no chaos. They did not detect chaos in the orbit of Pluto. And they interpreted it as, they subsequently wrote a paper saying that the orbit of Pluto is an example of so-called stable chaos. That is to say that there's some weak chaos, but in the big picture, the orbit parameters don't change a whole lot. There is some loss of information on some fine scale, but the overall shape and orientation of the orbit is perfectly stable for timescales comparable to the age of the solar system. And then subsequently, even longer term integrations became possible. Takashi Ito did this for his dissertation. In 2002, he published this paper with many integrations of the solar system, including Pluto, for timescales of something like 10 gigayears. So minus 5 gigayears in the past, 5 gigayears in the future. And here's a diagram from his paper where he projected the orbits of the outer planets in these 3D and 2D renditions. And in these plots, he's actually rotated in a frame where Pluto's perihelion is always on this on the positive x-axis here. And so you see that the shapes of the planetary orbits are pretty much preserved. There's a little bit of, if you have keen eyes, you can see that there's a little bit of fuzziness. There's some wobbling that goes on with the orbits, but for gigayear timescales, nothing dramatic happens. So the chaos is weak and it does not affect the broad stability of the solar system. So the answer is the takeaway from that is that Pluto's orbit is robust against small changes to orbital parameters. And so subsequent, since over the last several decades, we've also learned about exoplanets and more about the history and evolution of the solar system itself. And we know that the planets have actually undergone large changes to their orbits in their early history. So one of the questions that I was interested in was what happens to Pluto's orbit? What is the effect of changes to the planet's parameters, larger changes that would have happened in the early history? And actually, Pluto has had a role in revealing the orbital migration history of the planets. I wrote a couple of papers back in the early 90s making this point that Pluto's orbital resonance can be easily understood if we allow that Neptune had migrated outward rather than formed where it is today. And this is a simple animation to show that. So if Neptune migrated outward, so you saw Neptune going from a distance closer to the sun to its current distance at 30 astronomical units. And if Pluto had formed in a normal circular coplanar orbit, as Neptune moved out, its orbital resonance, the location of the orbital resonance, the 3:2 resonance, that is to say, the orbit where the period would be exactly 3/2 Neptune's orbital period, that location would have migrated out, and it would have not done much until a small body happened to get close to that resonant location. In other words, that resonance approached Pluto at some point, and then it trapped Pluto in that resonance. And this trapping in an orbital resonance is a phenomenon that's been well studied, particularly in the context of planetary satellites, like the moons of Jupiter. The Galilean moons of Jupiter are all in, most of them are in orbital resonances with each other. So this phenomenon of capture into resonance is fairly well understood. And so I propose that Pluto would have been captured into this resonance, moved along the resonance, and one of the consequences of being trapped and dragged along a resonance path is that the orbit becomes more eccentric. So it goes from a circular orbit initially to an eccentric orbit. And then mathematically, I showed that you could actually expect that if this phenomenon of migration of the planet and resonance capture occurred, we would predict that lots of small bodies, dwarf planets, minor planets, would be captured in resonances. and if other bodies existed besides Pluto. So at the time I wrote this, Pluto was the only one we knew about. But subsequently, we've discovered the Kuiper belt. There's a whole belt of small bodies beyond Neptune. And in fact, they are piled up in these orbital resonances. So this was a theoretical prediction. And there was a quantitative part of this, that the eccentricities of objects that are resonant with Neptune actually relate to how far Neptune migrated. Surveys of the outer solar system began to discover these Kuiper belt objects in 1993, and now we have more than 4,000 Kuiper belt objects known. This is, of course, the tip of the iceberg. These are very faint and hard to detect astronomically. We need the biggest telescopes to discover these. So there's probably hundreds of thousands of objects of similar sizes. Most of these are on the order, some hundreds of kilometers in size, and lots of them are actually in resonances with Neptune. And so this led to the idea that this was the observational evidence that Neptune had migrated outward. But Neptune doesn't migrate outward by itself. The other planets also migrate. And there's been a mathematical, quantitative understanding of that, roughly, about how much the other planets migrate, what the process is. So Pluto is one of these large population now of objects which are in this 3-2 resonance with Neptune, but there are other resonances that are occupied as well. The ones with Pluto in this 3-2 resonance are now informally called Plutinos. And by looking at these, the distribution of the eccentricities, how large the eccentricities get in these resonances, we now have an understanding that Neptune must have migrated out by at least 10 astronomical units. So it must have started out closer to 20 AU compared to its 30 AU distance today. So what caused this migration? The ideas we have are that in the late stages of formation of the solar system, planets, that is to say, early on, in the first few 100 million years of the history of the solar system, there were planets, and there were lots more debris in the solar system in the form of planetesimals. And this debris was cleared out through the gravity of the growing planets. So these planets were scattered, these planetesimals were scattered around, and then most of them were ejected. And part of that process, as part of that process, the solar system formed this Oort cloud of comets. So all of the material, or some fraction of the planetesimals, actually did not get totally ejected from the solar system, but remained bound at large distances. And we see that in the form of long period comets from time to time that arrive from this reservoir of comets that actually originated in the zone of the outer planets. And what's left over now, so during this scattering and ejection process, clearing out the debris in the solar system, the planets' orbits got moved apart from each other. Neptune moved out, the other planets also, Saturn and Uranus also moved outward. Jupiter actually moved in a little bit. And the reason for that is that Jupiter is the most massive of all our giant planets, and it's the one that's the most efficient in doing this ejection. Whereas the other planets are not massive enough to do this ejection and clearing on their own, but rather their role is to hand down all the planetesimals to Jupiter, and then Jupiter throws them out. It turns out that there's other observational evidence of this whole process of scattering and clearing out of the solar system. A close look at the asteroid belt, we find that there are asteroids that are missing, that we would expect to be there if the planets always occupied the giant planets always occupied the orbits that they do today. And so we can those missing asteroids can be understood if we allow that Jupiter and Saturn had migrated by amounts that are similar to what we infer from studying the Kuiper belt. As close as the moon, we can see craters on our own, on the Earth's moon. And the Apollo program back in the 1960s and 70s brought back samples from the moon, from which it was the laboratory study of those samples led to this conclusion that the moon had formed about 4.5 billion years ago, 4.45 billion years ago. Its crust had solidified, and then it was bombarded very heavily about 500 million years later. And so this has been, this heavy bombardment has been also linked to the era of planet migration. When the giant planets were migrating, they threw out more material over time, some of it from the asteroid belt, some of it from the Kuiper belt, and that all those planetesimals, some of them hit the moon, and they're recorded in the cratering record on the moon. So impact craters on planetary surfaces turn out to have two different crater populations. Those that are really ancient, dating back to about this era of heavy bombardment during the migration of the planets, and then everything subsequent to that. So one of the good things that this heavy bombardment did and the migration of the planets did was to clear out the solar system of most of its debris, so that there was heavy bombardment early on, and then subsequently only low rates of bombardment. So life on Earth actually appeared after this heavy bombardment era ended. And so we live in an era now that has only small probabilities and small impact rates on the planets because the migrating planets cleared out the planetesimals very efficiently. Okay, so let's get back to Pluto. So Pluto's dynamics is actually linked to everything that's going on in the solar system. The planets migrating, all the bombardment going on, and so forth. Okay, so back to Pluto, we have recently the New Horizons mission had a flyby of Pluto, and it turns out in the part of planning for that mission, there were greater astronomical observatories brought to bear to study the Pluto system. And it turns out that Pluto is actually a little miniature solar system. It has all these moons, not only the one that we'd known about previously, Charon, which is a large moon of Pluto, about half the size of Pluto itself. But it also has these 4 other moons, and then okay, so I'll just say Pluto turns out to be a really interesting object in its own right. But back to the problem of Pluto's orbital dynamics. Okay, so I mentioned that Pluto's orbit is eccentric, and its eccentricity can be understood through this resonance capture and the migration of the giant planets. What about its inclination? So it turns out Pluto's inclination is rather difficult to understand. How did it come about? If you do these, so this is a chart from a simple numerical simulation of this migration of the planets and what it does to small bodies in the outer solar system. And what you see here is two panels. The top panel is the distribution of semi-major axis, or the mean orbital radius on the x-axis, and eccentricity on the y-axis. And so in this simulation, we laid down particles like these planetesimals, like Pluto, uniformly in, as you see, this little gray line down at the bottom, in circular orbits, all the way from just outside where Neptune starts out, going out to some 60, 70 astronomical units. And then we let the planets migrate and do their scattering and sweeping of resonances. And at the end, this is what's left. So you see that a good part of the population is trapped in these orbital resonances, 2-to-1 resonance, 3-to-2 resonance, other resonances. And the eccentricities have been driven up. The red dot is Pluto. Now, if you look at the bottom panel, this shows the inclinations, what what are the inclinations of the surviving planetesimals. And we see that Pluto's inclination is up here. All the Plutinos that are trapped in the resonance have their inclinations kicked up, but there seems to be a barrier at about 10, 11 degrees. Nothing beyond that is, getting inclinations higher than that is rather difficult. It's kind of interesting that in the 2-to-1 resonance, one can get higher inclinations, and in some other resonances as well, but not in Pluto's. In any case, the distribution turns out to be rather difficult to get all the way up to Pluto's inclination. The actual observational data tell us that inclinations here can go up even higher. The observed objects have even higher inclinations, going up to 20 degrees and more. So this migration, as best as we understand it, accounts well for Pluto's and other Kuiper belt eccentricities, but not for the inclinations, and cannot account. It has great difficulty accounting for inclinations beyond about 10 degrees. More sophisticated models than the one I'm showing you here. This was a very simple model of the migration. More sophisticated models also do not provide very satisfactory answers for Pluto's inclination and in general inclinations of small bodies in the outer solar system. So we set out to understand this a little bit better. You've seen this part already, how Pluto's orbit or generally resonant orbits behave like this, that their perihelion does this kind of oscillation away from Neptune. Now, Pluto, it turns out, is involved in yet another oscillation or resonance in the third dimension. And so this is on this panel here, you see a sideways look. This is the z-axis on the vertical axis. And if you look sideways at Pluto's orbit, every time Pluto comes to perihelion, it's well above the plane of the solar system. And so its perihelion not only does this kind of oscillation in longitude relative to Neptune, we can call this an azimuthal libration. It also does a latitudinal libration. So its latitude when it reaches perihelion, its ecliptic latitude, is always near something on the order of 20, 25 degrees. So it bounces up and down a little bit. And you can see that in these animations on the right. When it gets to perihelion, it's always near the upper excursion above the ecliptic, at its highest excursion above the ecliptic. So we can call that a latitudinal libration of perihelion. You'll see, I'll show you a bunch of diagrams now. The azimuthal libration is characterized by the oscillation of an angle, a combination of the longitude of Pluto and Neptune. This is the resonant combination, and relative to Pluto's perihelion longitude. So here you see in time, this is 5 billion years propagation of Pluto's orbit. And this is this resonant angle. And you see that it's confined to a range roughly between 90 degrees and 270 degrees. So it oscillates around a mean value of 180 degrees. This latitudinal libration, I'll show you diagrams like these. These are polar diagrams where the polar angle is this what's called the argument of perihelion. This is the perihelion, the location of the perihelion, its angle measured relative to where Pluto crosses the ecliptic plane. And this angle librates, it oscillates about a value of 90 degrees. So in this polar plot, the distance from the origin is actually the eccentricity of the orbit. Okay, so Pluto also does this perihelion oscillation, this latitudinal oscillation, and we can see it in this polar plot. So both of these oscillations persist steadily on giga-year timescales. And this is also related to a resonance. It's a very subtle kind of resonance, and it's associated with the inclination and the eccentricity. And there's a numerical estimate that was made of what is the stable domain of these latitudinal librations. And it turns out that Pluto's orbit is actually robust to small, but not to moderate changes to its own orbital parameters. So remember I mentioned this weak chaos. So the weak chaos is weak in the sense that small changes in Pluto's initial conditions, Pluto's orbit is stable against those. But if you make significant changes, it's not so stable. Okay. And so there's a domain of the range of oscillations, these two azimuthal and latitudinal oscillations. There's a finite domain for which these nearby Pluto-like orbits can persist for the age of the solar system. Okay, so what I'm going to now talk to you about is these azimuth, is the latitudinal librations. I'm going to focus on the latitudinal librations because those are not well understood, in contrast with the azimuthal librations. Okay, so this is related to a phenomenon. This is thought to be related to a phenomenon called the VZLK phenomenon in the three-body problem. The VZLK refers to one Zeipel, Lidov, Kozai. These were mathematicians. One Zeipel lived something like 100 years ago, a famous mathematician and celestial mechanician, worked on many different things in astronomy, in astrophysics. And amongst those, he discovered this number of interesting effects in the three-body problem. And these were lost to memory and rediscovered in the 1960s when the space program got started. Lidov was a Russian mathematician, and Kozai was a Japanese mathematician. And actually, Kozai is still around, I believe. They're also known as the Kozai resonance or the Lidov-Kozai effect. And what this is the following. When you, in the three-body problem, that is to say, if you have a small body orbiting the sun, let's say, or some central body, and there's a distant perturbing object, that's our, let's say, a planet, and this is an asteroid, then if the asteroid's orbit is not in the same plane as the perturber, as the planet's orbit, an inclined orbit, if the orbit is inclined above some critical inclination, then circular orbits of the asteroid become unstable. Okay, so circular orbits that are highly inclined are unstable. They start flopping around. Then the eccentricity and inclination get trade off. So the high inclination gets pumped into a higher eccentricity. And so the eccentricity goes, or the orbit becomes more and more elliptical as it gets to smaller inclinations, and it oscillates back and forth. But eccentric orbits turn out to be stable, and they can undergo these oscillations, these stable librations of these latitudinal oscillations. And so there's a trade-off between eccentricity and inclination. And so this is a phenomenon that was discovered in the three-body problem back almost 100 years, more than 100 years ago. And it's actually been exploited in some in spacecraft navigation. This is a cartoon from the, I think this was in the 1970s, when Lidov discovered this for spacecraft trajectories. He pointed out that spacecraft trajectories that were highly inclined, almost polar orbits, would be unstable. And so what this cartoon is showing is that if the Earth's moon had been in a polar orbit, it would have fallen down on the Earth. It would not have been stable. Okay, so this phenomenon identifies this critical inclination, and the critical inclination for the problem where the perturbing planet is outside versus inside, the critical inclinations are different. And in the case of Pluto, let's see, here's the case of Pluto is the outer object, and it's being perturbed by planets, Neptune in particular, that are interior to it. And this problem is a little bit different than the classical problem that Kozai and Lidov studied, where the perturber is far away. And when the perturbers are interior to the small body's orbit, then the critical inclination turns out to be rather large. It's about 60 degrees. So the orbits have to be, the small body's orbit, Pluto's orbit, should be about 60 degrees in inclination to have this to do these stable oscillations. And of course, Pluto's orbit is not that inclined. Okay? It's not above this critical inclination. So as per the theory, the critical inclination is about 57 degrees, but Pluto's inclination is only 17. And yet Pluto is doing this VZLK oscillation. Okay, so how does Pluto's VZLK oscillation come about at this lower inclination? That's what we set to find out. And what we found was that Neptune's perturbations, including its resonant perturbations, are not sufficient to do this. And we carried out a number of numerical experiments, simple numerical experiments. What we did was we said, well, if we take all the giant planets and propagate Pluto's orbit under the perturbations of all the giant planets, then Pluto undergoes both of these oscillations, the azimuthal as well as the latitudinal perihelion oscillations. So what is the role? And it's clear that if you just do Neptune's perturbations, Pluto is not able to do that. So what's the role of both individually and collectively, the role of Jupiter, Saturn, and Uranus on Pluto? And all these panels show the propagations done with these something like 5 gigayear propagations done with subsets of Jupiter, Saturn, and Uranus added to the three-body problem of the Sun, Neptune, and Pluto. And what we found was that if you take away any one of the other planets, Jupiter, Saturn, Uranus, or add only one or two of those planets, then Pluto's orbit is unstable. Okay, so here, for example, if you add Uranus, Pluto's orbit becomes unstable instantaneously. It doesn't, neither the azimuthal nor the latitudinal librations persist. But if you add Jupiter or Saturn, you get a little, for some period of time, you get stable oscillations, but they don't last forever. Only Jupiter, it turns out, is actually stabilizing. Here you can see that under Jupiter's perturbations alone, Pluto's orbit is stable, although it does not do the latitudinal librations. Okay, so in the end, we found, so with all these experiments, the takeaway is that it turns out Uranus is extremely destabilizing on Pluto's resonances, all these oscillations, whereas Jupiter is a stabilizing influence. However, no subset of these three other planets, Jupiter, Saturn, and Uranus, will actually allow Pluto to do these latitudinal librations over gigayears. We need all three planets to do that. So what is it about all three planets? How is it that they're allowing Pluto to do this, in particular, this oscillation? How are they propping up Pluto in this inclined orbit? Well, if you think about the role of Jupiter, Saturn, and Uranus on Pluto, Pluto is far away. These planets are zipping around very quickly. Jupiter is going around every 12 years, while Pluto is leisurely moving around with an orbital period of 250 years. So from the point of view of Pluto, the perturbations of Jupiter, Saturn, and Uranus can be approximated as rings. And why do we bother to do that? After all, we can do these full numerical propagations. The problem is that doing those full numerical propagations with a range of all the parameters of three planets like Jupiter, Saturn, and Uranus involves something like 21 separate parameters. So if you want to explore the effect of Jupiter in a slightly different configuration, and Saturn and Uranus, that's a lot of parameters to explore. It's computationally not feasible. By approximating them as rings, we collapse those 21 parameters into a single parameter. And that's basically, these rings behave like the effect of the sun, which is oblate. Okay, so the rings add to the equator of the sun, like an extra belt around the sun, and we can parameterize that as an oblateness parameter, which is just, it just depends on the mass ratio of the planet to the sun and how big its orbit is relative to the sun's diameter, the sun's radius. And so each planet then can be represented by an oblateness, and altogether we add up these oblateness factors. And so there's a single oblateness of the sun that we can represent these three planets' effects on Pluto. And then we asked, is there some range of this J2 parameter that supports Pluto's latitudinal librations? And so I won't go through it in detail, but it turns out that this modified three-body problem with an oblate sun, we explored this numerically and found indeed there's a range where these, for most of that range that we explored, Pluto will not do these latitudinal librations. There's only a narrow range of this oblateness parameter that will allow Pluto-like orbits to do these latitudinal librations. And you see that here, this is a log plot, a log scale of the J2 parameter going from 1 to 10,000. And when the J2 parameter is small, that latitudinal libration doesn't occur. You get a steady rotation. When the J2 parameter is larger than about 3,000, again, you get rotations rather than oscillations of that critical angle, the argument of pericenter of Pluto, and those are in the opposite direction. But there's this range, this nice, narrow range here, which is around about 1,300 to about 1,600 in J2, where these steady and stable oscillations, latitudinal oscillations, are possible, and they're bounded by regions where where this argument of pericenter of Pluto has chaotic motion. Okay, so here it's strongly chaotic, and of course where the actual effective J2 of the planets lies in this green zone. So Jupiter, Saturn, and Uranus create this effective J2 that lies right in the middle of this, or actually to one side of this green zone in J2. So this was this was somewhat of a surprise. What it means is that the arrangement of Jupiter, Saturn, and Uranus is rather fortuitous to support Pluto's long-term stability. So not any arrangement of Jupiter, Saturn, and Uranus, which could also be in itself stable, would support Pluto's stability. And this gives us some handle on what kind of planetary system can support these special oscillations that Pluto undergoes. And it's on the order, if you change the orbits individually of each of these planets by less than 10%, or you can, or on the order of 20% in the case of their masses, that's all the room we have to play for the architecture of the solar system, for stability of these resonant orbits in the Kuiper belt. Now, if you look at we saw previously, that the planets have migrated. We've understood from other directions, other pieces of evidence, that the giant planets have migrated over time in their early history. During that migration, their effective J2 parameter would have changed, and it would have started out smaller because the planets were closer together, and it would have increased to its present value. And so during that process, we can actually get some new constraints, potentially. This is an area we haven't explored sufficiently yet. It's still open for research. So one of the new things we can get is that previously we had good constraints on, or good understanding of how much Neptune had migrated and how much Jupiter had migrated, but the constraints on Uranus and Neptune were somewhat fuzzier. And here we can at least say that, or conclude that if Uranus had migrated by more than 5 astronomical units, then Pluto-like orbits would have been unstable, would have made transitions from unstable VZLK oscillations to stable VZLK oscillations. And the meaning of that and its implications, we still need to work out. Okay, so I'll summarize now. I think I'm okay, not too bad in time. So in trying to understand better the problem of Pluto's inclination, we understood something different, that the orbital arrangement of Jupiter, Saturn, and Uranus is actually quite delicately balanced for the stability of a good fraction of the Kuiper belt objects that are in resonances with Neptune. And the problem of Pluto's inclination actually is still outstanding. It needs more research. It's a very subtle problem. The phase space part of our investigations has also revealed that the phase space around these resonances is actually very, very complicated when you go in the third dimension. And so we're still looking into that. So I'll stop here. I'd be happy to take questions. I think you're muted, Tasia.
Sorry. Sorry. Okay, I was trying to get back. I didn't understand. I couldn't unmute. Okay, sorry. Thank you so much for the presentation. We now have time for questions from the audience. You can raise your hand, or if you'd rather, you can put your question in the chat and I'll read it out. If you're on YouTube, you please feel free to write the question in the chat as well, and I'll read it out to Renu. Give a moment. I have a couple of questions, but I always like to give the chance for others to ask first. Okay, I think I'm going to start then. So in the beginning, there was actually, I think it's a term or a mechanism that I don't really understand. You mentioned that the planetesimals, they get ejected, right? In the beginning. So how exactly does that happen?
So planetesimals that are crossing or approaching Neptune's orbit. So most of the planetesimals that survive after the very early stages of the solar system, most of the mass of those planetesimals is going to be beyond Neptune, because the interior ones have already been scattered and accumulated into the planets. So the remaining planetesimals, some of them will have orbits that have perihelion near Neptune, and there they get little kicks from Neptune, and their orbits become more elliptical. We see that, actually, even now, we see that in the orbits of the short period comets. They have close encounters with the planets, and their orbits become more elliptical. Their perihelion drops to smaller values, and then they can cross Uranus. Uranus gives them kicks. They fall further down towards Saturn. Saturn gives them more kicks. So it's like a chain reaction. They start out from outside Neptune's orbit, and they successively get these kicks from Neptune, Uranus, Saturn, until they end up with perihelion near Jupiter's orbit. And then Jupiter is so massive that it gives them a big kick, and then most of them end up in hyperbolic orbits, ejected from the solar system. It's the same process we actually use in spacecraft navigation. You might have heard of gravity assists for spacecraft. And those so for example, this past Sunday, the Lucy spacecraft, which is going to be exploring asteroids, the Trojan asteroids of Jupiter, it had a gravity assist with Earth. It came back in its orbit, came very close to the Earth, and got a gravity assist to go into a bigger orbit, which will allow it to reach Jupiter in its subsequent trace. Did you hear about that on the news? No? Okay. So it's a well-known phenomenon. It's a well-known mechanism that's used to kick orbits around.
So basically just bounces from
in the case, yes, in the case of the Kuiper belt objects, they just bounce their perihelion down, down, down. They kind of step down in perihelion. Their orbits get more and more elliptical to smaller and smaller perihelion until they get to a perihelion near Jupiter and have a close encounter with Jupiter when they get thrown out of the solar system.
Is the process the same for the more central belt, the one between Mars and Jupiter?
Yes, those asteroids also, yeah, in the asteroid belt also there are these kinds of instabilities and the orbits become more elliptical. There, the reason is actually resonances alone. The resonances with Jupiter produce strong chaos and the orbits become eccentric because of that. There, the aphelion sometimes gets close enough to Jupiter to be able to eject asteroids. But more often in the case of asteroids, the orbit perihelion gets small enough to get near Mars or Earth. And then very often they end up hitting the sun or the terrestrial planets.
That's very interesting. Thank you. If I can ask another question. So to the participants, you can raise your hand up at any moment and then I'll call on you. So my question is, like in the previous slides, when you were talking about the 3 planets and how you reduced them to rings instead.
Right. Up here?
Yes, this one. Yeah. Okay. So the moment you do that, do you then have a 2-body problem instead of a 3-body one?
That's right. We don't actually, we go beyond the 3-body problem. Here we have, what we were doing was, I've not displayed Neptune here, but Neptune is also in the picture. So we have the Sun, Neptune, and Pluto. And the Sun is not a point mass, it has an oblateness. So it's a 3-body problem with an oblate Sun, Neptune, and Pluto.
Okay, I thought it was the 3 orbits that got converted into rings. Okay, so okay, that makes sense then. Thank you. Okay, I have maybe a last question.
Okay.
Okay. So when you were talking about Jupiter's orbit, you had these nice plots that showed, sorry, not Jupiter, Pluto's orbit. So there was like a more circular one, and then there was like a side view.
This one?
Yes. And then there's a base-like structure. So like it goes up on both sides, but then it doesn't go down past this particular value.
Mm-hmm.
Is there a reason for that, or is it just the angle that we're looking at?
So this is the trace of Pluto's orbit in this rotating frame, right? So Neptune is stationary here. So we are going into a frame which is co-rotating with Neptune. And in that frame, Pluto is doing, you saw this animation here, right? Let's see if I can get it back. Yeah, you can see that animation there. So here we are looking top down, and here we are looking sideways. And I think your question is, why doesn't it go further below?
Yes, or even further up, because it just has like a maximum and a minimum. Like
right, and that has to do with its inclination. So given its orbital inclination, it has a maximum height above the ecliptic and a minimum below the ecliptic, right? So let me actually, maybe another way of seeing that is by looking not in the rotating frame, but in a normal, what we are used to. So if we look at this, so this is Pluto's orbit plane. And when it's at perihelion, it's up near the top over there. And when it's at aphelion, it's up near the bottom here. And that's the extent of how far it goes up and down. It doesn't go farther than that up, and doesn't go below that. Does that make sense?
Yeah, I think I got a bit more confused because of how it was moving all over the place. Okay.
Yeah, so this is, rotating frames are not the most intuitive. It's like put yourself on a carousel in a fair and the world looks different, right?
This is very interesting. Thank you. We have time for more questions from the audience. Sorry, let me just check YouTube. Okay, no. So if there are no more questions, I think we can wrap this up. The presentation will be available on the website and on Linea's YouTube channel. Thank you everyone for attending, and a very special thanks to you, Dr. Malhotra. Everyone have a great day, stay safe, and I hope to see you all again in our next webinar.